shapes.
And they're the building blocks of modern civilization.
We wouldn't have televisions, we wouldn't have automobiles, we wouldn't have buildings without the mineral riches that we have.
But could rocks and minerals also solve the greatest mystery of all time? The origin of life.
The rocks we pick up tell a story that life couldn't have occurred without rocks.
Could cold, lifeless stone hold the key to every living thing on Earth? From Australia to Morocco, Nova goes around the world and back in time to investigate the origin and evolution of life.
Look at the rock and you think, oh, nothing. But this holds the signature of life.
From its first spark
People were saying they made Frankenstein in a test tube.
to the survival of the fittest.
These were immense creatures, sharks that may have been 50 or 60 feet.
Was it the secret link between rocks and life that made the difference? Life's Rocky Start, right now on Nova. The ancient market of Marrakesh. A chaotic, colorful gathering place teeming with life for thousands of years. The perfect place to ask, how did this exotic, beautiful, and sometimes bizarre thing called life begin? How did Earth go from a lifeless, molten rock to a living planet full of diverse and spectacular creatures? It's a question that has long perplexed scientists. Now, Robert Hazen, a geologist, is trying to show we are missing an essential ingredient in the recipe for life.
Look at that name, Kelsey.
Rocks.
Nothing seems more lifeless than a rock. It's inanimate. It's the antithesis of a living thing. But we're beginning to realize that rocks played an absolutely fundamental role in the origin of life.
Hazen is out to expose a secret relationship between rocks and life that helped drive both the origin of life and its evolution into complex creatures.
This is a very new set of understandings. And the more we look, the more we see that life depends on rocks, rocks depend on life. This has been going on for 4 billion years.
As a geologist, it's no surprise that Hazen is searching for answers written in stone. But is he right? Are rocks the missing spark of life? The history of Earth is unimaginably long. If it were sped up to the equivalent of a single day, all of humankind, from the earliest skeletons to the invention of the iPhone, would have occurred in only the last 4 seconds. Dinosaurs were still roaming Earth about 20 minutes before that. But the creation of our planet occurred more than 23 hours earlier. 2 cycles on this clock, or 4.5 billion years ago. Comprehending Earth's vast history is a formidable task.
There's 4.5 billion years of change, but you can divide it into half a dozen ways of describing Earth through time.
Bob Hazen has come up with another way to visualize Earth's long history that reveals this special relationship between rocks and life. He has divided it into 6 stages, each represented by a different color. To understand how we ended up with green Earth, the planet we now know, requires us to turn the clock back to before there was any life at all. Stage 1 was the creation of a black Earth. Back in Morocco, Hazen and Adam Aronson, a meteorite expert, seek out a small rock from the beginning of our cosmos.
Wow, look at this pile here.
These are meteorites, rocks that have fallen from space.
This is Tamdach. This is the one that fell 20 kilometers up the road from here. You saw it fall.
A recent meteorite fall in Siberia was captured in videos that have shown up on YouTube. Other space rocks have ended up for sale here in Morocco.
Say you buy this without doing tests.
I'll drop the cash right now if you give me a good price. That's one of the
Meteorites here can sell for tens of thousands of dollars. That may seem a steep price for a lump of rock, but these are some of the very oldest objects in our solar system.
This is the oldest object you could ever hold in your hand. It's 4.6 billion years old, and it was formed before Earth formed. This is the very first solid material, the very first rock in our solar system. And these came together to build all the planets.
Our Earth was created out of the rocks and dust present at the start of our solar system. Over time, small fragments of orbiting rock collided, coming together into the planets circling the Sun. At first, Earth was molten with temperatures in the thousands of degrees. But in the cold vacuum of space, this hot rock began to cool and change. Nothing, not a speck of dust, is believed to have survived from the period of Black Earth. It was a hellishly unpleasant time. Volcanoes spewed hot lava from deep inside the planet. When it cooled, it covered Earth with its first rock, called basalt. And it was black. It seems like a desolate landscape. But some ingredients that life will need are already here in these rocks. Look inside and you begin to understand how intriguing even an ordinary rock is.
Every rock, you slice it open, you look inside, there's something special.
Rocks are made up mostly of minerals, which are crystals like quartz or diamonds. Looking through a microscope at super thin slices of a rock lets you see its mineral composition. This is the rock peridotite, made up of small crystals including olivine and pyroxene. Even a simple black basalt rock spewed from a volcano becomes a patchwork of colorful minerals.
It's sort of like a fruit cake. You know, slice it open, there's nuts, and there's dried fruit, and maybe some lemon peel. It's made of lots of little things, and it's not until you slice into that fruit cake you see all the stuff inside that makes it special.
What makes them special is not only their beauty. Minerals have remarkable chemical and physical properties and are a source of many of the elements, nature's building blocks. That is why they're essential in our modern world to make everything from skyscrapers taller to mobile phones smaller. Extract the element molybdenum from the mineral lipidite to make steel stronger. Or add a pinch of cobalt, and your iPhone battery will last longer.
Minerals are the fundamental building block of societies. We wouldn't have televisions, we wouldn't have automobiles, we wouldn't have buildings without the mineral riches that we have.
So were the remarkable chemical properties of minerals also key in creating life? If so, Earth would need more than it started with. It's estimated that the meteorites that formed Earth had only about 250 minerals, sort of a chemical starter kit containing many of the elements. Then, in the intense heat and pressures in the creation of our planet, new minerals began to form. This changed the appearance of our Earth from black to gray. Yosemite National Park is a relatively new piece of Earth. But the kind of rock that makes up these dramatic cliffs goes back much further. These huge walls are granite, containing minerals like quartz and feldspar. Granite became the foundation of our continents, leading Earth into the Gray Period. At this point, Earth is still a long way from the glorious diversity of plants and animals that makes Yosemite so picturesque. But the stage is set for the next character in our planet's story. Water, which will turn Earth blue.
Water plays a central role in every model for the origin of life. That's because water is such a great solvent. All these different kinds of molecules can be floating around the water, and then they have the potential to interact together. The starting point is the water.
So when did Earth cool enough to have liquid water, this element key to life?
One of the biggest unknowns in this whole idea of going from black to gray to a blue water-covered Earth is how quickly it happened. The timing is a big mystery.
The Pilbara in Western Australia is one of the oldest places on Earth, and so one of the best places to solve the mystery of the planet's first oceans. Hazen joins an all-star team of geologists, including Martin van Kranendal from the University of New South Wales and John Valley of the University of Wisconsin. Valley is collecting rocks that could hold clues to when water first appeared.
We could get zircons and other minerals that date all the way back to 4.4 billion years old, hopefully.
Some rocks here contain sand-sized grains that weathered from even older rocks. 1 in a million, literally, is a crystal called zircon, one of the longest-lasting materials in nature. Zircon is a popular gemstone, but the microscopic zircon found here is even more precious.
Zircon crystals are especially amazing. Gemstone zircons, of course, are valued, but these tiny ones that the geologists value are microscopic. They make a lousy ring, but they tell an incredible story.
To tell that story, John Valley must first find the tiny crystals, the ultimate needle in a haystack.
If you want to find a needle in a haystack, first thing you do is you burn down the haystack. Then you sift through the ash to look for the needle.
Rocks are pulverized into sand-sized grains and sorted by weight in a machine developed to pan for gold. The gold that Valley is looking for are heavy zircon crystals, which get channeled into different tracks. Then, grain by grain, with a very steady hand, thousands of small crystals are sorted and analyzed. The chemical structure of a zircon crystal holds evidence of both the environment and the age when it formed. Some of these tiny crystals go very far back, just over 100 million years after Earth formed. They're the oldest pieces of Earth ever discovered, so they could shed light on what our young planet looked like.
It's totally amazing to me. To hold this grain of sand in the palm of your hand is literally to see back through time. is a time machine.
Valley expected these crystal time machines would confirm the long-held view that the young Earth was covered in molten lava, still cooling after its violent formation.
So I think the zircon on the left looks very promising.
So what he discovered was shocking, because this type of zircon, created 4.3 billion years ago, could only have formed in the presence of liquid water. But how could there be water if Earth was still hot and hell-like?
The implications were that the early Earth had water, it was cooler, and it was wet. It's starting to look very much more familiar.
And if water is a key starting point for life, could there be life that early, too?
The science of the zircon is telling us that the Earth, for a very, very long time, was a habitable environment. Not necessarily that there was life then, we don't know that yet, but there's no reason why there couldn't have been life as early as 4.3 billion years ago.
So if life were possible that early, it begs the question, how did life begin? In 1871, Charles Darwin speculated in a letter to a friend that a warm little pond might be life's birthplace. A warm soup of chemicals bathed by energy from the sun would have been, well, comfortable for molecules to come together in new ways and create life.
Darwin was way ahead of his time. A nice little warm soup is going to get you a long way.
Jeff Bada of the Scripps Institution of Oceanography in San Diego has spent his career working to understand the early Earth soup of chemicals. He began under the direction of perhaps the most famous scientist in origin of life research, Stanley Miller.
There are in the history of science turning points where we suddenly see the history of Earth and life differently. In the early 1950s, Stanley Miller, the eager graduate student, and Harold Urey, the Nobel Prize-winning mentor at the University of Chicago, conducted this astonishing experiment where they made an early Earth environment.
It was like this sort of a Frankenstein-type apparatus, but actually it's a very carefully thought out design.
Bada sets up a modern-day test of the 1950s experiment on Miller's original lab equipment.
One flask contains water. That's to simulate the ocean. The other flask has just got the gases in it. So this is the atmosphere.
Just as it does in nature, water from the ocean evaporates and then rises into the atmosphere, where it condenses and then returns to the ocean. Miller simulated what he believed to be the atmosphere of early Earth with different gases, like ammonia and methane. Then he added a spark of genius.
Miller and Urey decided to use a spark to simulate lightning because that's such a ubiquitous process in the atmosphere of the Earth.
That was the real inspiration. These electric sparks acted like simulated light.
The energy from the spark of lightning breaks down the gas and water molecules, so they can undergo further chemical reactions.
To their astonishment, when they turned this apparatus on, after only a couple of days, you started seeing this pink color developing. Then, a few more days, black, oily goo is forming around the electrode.
The electrodes get covered with new substances. Organic compounds usually associated with life.
And it wasn't just any organic compound. It was amino acids that make proteins the ingredients for life.
Amino acids are the building blocks of life. They form proteins, which are the key component of muscles and other tissues.
People thought, this is a key step in the origin of life.
And you really believe that you can bring life to the dead? That body is not dead. It has never lived. I created it.
The experiment raised the fear that a Frankenstein creation, like in this classic film, was just around the corner.
People were saying they made Frankenstein in a test tube.
It's alive! I know it feels like being
Had Miller and Urey cooked up life in a test tube?
Many of the news headlines were saying life created in the laboratory, life created in a test tube. Well, of course that was wrong. The real news was you made these compounds that are part of life.
By creating amino acids, the Miller-Urey experiment seemed to confirm that Darwin was right. Life must have begun in a shallow pond. But then, 24 years later, a shocking discovery radically challenged that idea. On the dark ocean floor, more than a mile below the surface, explorers found hot, mineral-rich hydrothermal vents, like underwater volcanoes. Temperatures reached more than 600 degrees. And yet here, life was thriving, not off the sun's energy, but through chemical energy from the vents.
No one realized that life could thrive without sunlight. Here you have this extreme temperature and this extreme pressure, and so you have to shift your perceptions and realize that just because it's extreme to us doesn't mean it's extreme to those microbes.
Instead of the warm, shallow pond, could this dark and unlikely environment be where life began? To answer that, Hazen decided to try creating life's building blocks in the conditions of a deep-sea vent.
My first thought was, gee, why don't we do a Miller-Urey experiment, but do it at high temperature, high pressure?
Hazen's laboratory is at the Carnegie Institution for Science, which is famous for experiments that simulate the intense pressures deep inside Earth, with powerful tools called pressure bombs.
And they're called bombs for a reason, because things can explode.
Hazen and his colleagues adapted these pressure bombs to model the environment of the deep-sea vents in a small gold tube. What they discovered came as a surprise. Nothing happened.
You can take basic gases, nitrogen, CO2, maybe some sulfur compounds. You can mix those, you can put them in a gold tube, you can heat them up. You don't get much that's very interesting.
Simply squeezing and heating the ingredients had little effect. Hazen was missing the spark, like in the Miller-Urey experiment, the thing that kickstarts the chemistry.
So he said, what's going on? What's different? Well, look at the natural environment. It's all these rocks and minerals. Let's try putting some rock and minerals in.
They recreate the earlier cocktail, but this time grind in powder from rocks and minerals. But will Hazen's beloved rocks do the trick? They run the experiment again. And this time, the atoms reform into new organic molecules, including amino acids.
As soon as you put powdered rocks and minerals into the gold capsules, that all sorts of really amazing things started happening. You made organic molecules. They became more stable. They lasted longer. And it really pointed us in the direction of saying, aha, this has got to be part of the story.
While scientists still argue if life began in shallow ponds or deep-sea vents, both sides wonder what part of the story did rocks and minerals play. One possible answer may be found in London, in the powerful properties of mud.
Most people will be familiar with the material. It's very gungy. That's perhaps a British word that refers to something which is soft and unpleasant generally.
Peter Coveney of University College London is busy playing in mud at a very sophisticated level. He has created powerful computer simulations that can track the precise movement of up to 10 million atoms. Mud can contain clay, which is made up of some of Earth's most common minerals. What makes it so gungy, and perhaps essential in the origin of life, can be seen deep in its atomic makeup.
You can see here the basic structure of any clay. It's comprised of a large number of stacked sheets, like a deck of cards.
Sheets of clay have spaces between them that fill up with water and other molecules. These extensive surface areas can help create more complex molecules, potentially even an RNA, an essential part of life's genetic code.
One of the most challenging questions in the origin of life is how we get from the simple building blocks to the complicated structures we know are fundamental to living systems. Clays provides a clear mechanism for achieving that.
These simulations show that the secret to clay lies in its surfaces.
The surfaces of these minerals are incredible. They do all sorts of chemical tricks.
Hazen says minerals, like clays, illustrate a fascinating aspect of chemistry, because the surface, where reactions take place, can be as important as the ingredients themselves.
The most exquisite chemistry occurs at surfaces. Your body, your cells, are almost entirely surfaces on which chemistry takes place. So when we think about the origin of life, the minerals sort of replace surfaces you have in your body to do that chemical work.
We are finally beginning to understand the secret role minerals could have played in life's origin. They provided some of the ingredients and surfaces where important chemical reactions take place. So when in Hazen's color phases did all this happen? One of the best places to figure that out is back in Australia, where Hazen and team are now searching for signs of Earth's earliest life.
I can't believe these rocks are 3.5 billion years old. They look like they formed last week.
Martin van Krenendonk leads the team to a very unusual rock formation.
You get your eye cast enough, you see them all wrinkly, laminated, black.
Yeah.
And then if you look a bit further back, you see a very large dunkel structure.
There's no obvious way that a chemical or physical process would form that.
Exactly.
These strange shapes are fossilized remnants of life, called stromatolites, beautifully preserved in these ancient rocks.
This is an amazing spot. We're actually looking down on the surface of the ancient Earth here. This was the sea floor 3.4 billion years ago. I can see it in action. It's like a snap frozen instant of time.
But billions of years have taken their toll. To really understand stromatolites, we have to go nearly 800 miles away. David Flannery, a geologist, has come to Shark Bay in search of their very distant descendants. Just below the surface, he finds a series of round black mounds, living stromatolites.
Modern environments like these, they're very rare, but they're really the key to interpreting what we see in the very early fossil record. Without environments like these, we wouldn't know how stromatolites were built.
Stromatolites are something like coral, a hard mineral structure that has been built layer by layer. A closer look reveals the builders. Microbes, single-celled life.
The living part of stromatolite is on surface with a living microbial mat is building up the structure layer by layer at less than a millimetre per year.
The top layer of these stromatolites is alive, with microbes that perform a remarkable trick. They capture minerals and sand in the water and biologically cement them, layer by layer, into solid mounds. The results can be seen in Shark Bay today, and in the ancient fossils.
Yeah, let me introduce you to this outcrop. It's just spectacular to be able to see this.
And this outcrop is unique.
See they're still asymmetric?
Van Crandonk has dated this stromatolite to 3.5 billion years ago. This is the very oldest fossil of life on Earth.
We all want to know where we come from, where life originated, how long ago, in what form, and this is the oldest direct evidence we have for life on Earth.
But while stromatolites are the earliest fossil of life we've found, that does not make them the very first living thing. In fact, Van Crandonk thinks that by the time stromatolites appeared, life's party was already in full swing.
There are whole communities and colonies that are building fantastically complex structures. So we've actually come in pretty late to the game. There's a lot that's gone on before us to get to this stage. And it's this complexity that tells us that life probably originated on Earth very early.
So if these very early fossils are too complex to be the oldest form of life, is it possible to find something earlier? That's what Ruth Blake, a geologist at Yale University, is trying to figure out by turning to the geological equivalent of a crime scene investigation.
The crime has been committed, the criminal is gone, but they've left behind some indicator because they've changed their environment.
Blake is analyzing some of the oldest rocks on Earth, like this ground-up one from Greenland that formed at the bottom of an ocean. She is looking for a chemical signature of life left by microbes, including bacteria.
What we start with is our ocean trapped in the rock, and our biosignature is somewhere in here. We have to get it out.
In the lab, Blake and her team dissolve these rocks and extract molecules that are the chemical signature left behind by ancient microbes. All life, like these microbes, consumes nutrients to produce energy. The leftovers carry the chemical footprint of life. Even today, we humans leave behind chemical footprints.
When we breathe, for example, we're taking in oxygen and we're exhaling CO2 and water vapor. That water vapor interacts with your environment.
Amazingly, rocks from 3.5 billion years ago, at the time of the stromatolites in Australia, also carry a strong chemical footprint of life. But when Blake analyzes the Greenland rocks from 300 million years earlier, she makes a tantalizing discovery.
As far back as 3.5 million years, we see a strong biological signature. The older rocks are approaching that, but not quite there. But we do believe that we see something there.
Blake believes she has detected the faint signal of life at 3.8 billion years ago, only 700 million years after Earth was created, early in the blue phase. There is still much that we don't know about our early planet, but some things are becoming clearer. If you could transport yourself back in time about 4 billion years, parts of our Earth might not look too different than this Southern California beach, minus the surfers and Google. You could stand on cliffs, probably of granite, overlooking oceans that were increasingly rich with minerals and early microbial life. But you would quickly die in a great deal of pain, suffocating in the heavy atmosphere rich in nitrogen and carbon dioxide, but lacking in life-giving free oxygen. Then, something truly astonishing happened. Those harmless-looking microbes floating in the water or on stromatolites started to change everything, turning Earth red.
Wow. Oh my God, this is amazing. There aren't many places on Earth you can see something like this.
A remnant of red Earth can be seen in Australia at the Hammersley Basin in Karanjini National Park. In these rocks, Hazen finds a startling consequence of early life as it began to thrive and evolve.
What we're seeing here is one of the greatest tricks that life ever figured out. It knows how to take sunlight and convert it to energy.
Microbes, like those in the stromatolites at Sharp A, eventually began to live off the sun's energy through photosynthesis. That led to a dramatic rise in a gas that Earth was not accustomed to: oxygen. While to us, oxygen is a life-giving benign gas, to a world not accustomed to it, oxygen created a dangerously corrosive cocktail. The early oceans were filled with dissolved iron. The new oxygen reacted with that iron, and it began to rust and sank to the bottom of the sea.
These little microbes, they're microscopic things. You wouldn't think they could do all that much. But when they produce that oxygen, and the oxygen reacts with the iron in the oceans, you get the world's largest deposits of iron, thousands of feet, covering hundreds of square miles.
These formations cover a vast area with trillions of tons of iron ore. That is an unimaginable consequence of trillions upon trillions of microbes breathing.
It's a fundamental change in the chemistry of Earth. It's a consequence of the rise of oxygen.
The rise in oxygen that rusted iron and sent Earth into the red phase also created many new minerals.
As a mineralogist, when I look at Earth history, I see big transitions. I see the moon forming impact. I see the formation of oceans and so forth. But nothing matches what life and oxygen did to create new minerals.
Some estimate that the meteorites that formed Earth began with only about 250 minerals. Today, there are more than 5,000. Hazen believes that 2/3 of all minerals that now make our planet were created by the introduction of oxygen. And most of that was in turn created by life.
It's mind-boggling. Rocks create life. Life creates rocks. They're intertwined in ways that are just now coming into focus.
But the road ahead for life, and for rocks, would not be easy. As we head into the next phase of Earth, new continents formed and then broke apart, which may have created dramatic extremes in the climate. Earth plunged into an icy freeze, turning it white. In these frozen conditions, life was nearly wiped out. Fortunately, active volcanoes still poke through the icy veneer, billowing out carbon dioxide, or CO2. Like a thermal blanket around our Earth, this kept heat in and rescued life.
Life all but shut down. And then the CO2 rises and rises, and the greenhouse effect gets hotter and hotter, and suddenly the planet melts.
Cycles of these snowball hothouse conditions had profound consequences for life. One result was more oxygen, which eventually allowed for bigger animals. The dramatic changes during White Earth would bring us to the present phase, starting about 540 million years ago. A living planet, filled with diverse plants and spectacular creatures. But those life forms are pitted against each other in the survival of the fittest. And rocks can make the difference between life and death. That struggle can be seen back in Morocco, at the edge of the Anti-Abyss Mountains. Here, Bob Hazen and Adam Aronson are looking for evidence of an evolutionary trick that shows once again how life and rocks took a big leap forward together. $520 million years ago, this valley was a shallow ocean, filled with new forms of life. This is when the diversity of life on Earth exploded, all thriving in a living sea.
So if you were a scuba diver and you dove down to this reef, you'd see all kinds of life swimming around. It would be really amazing, probably very colorful too.
There is one creature that dominates this ancient reef that Hazen wants to find.
Nothing there. Nothing there. And nothing there.
Fossil hunting is a game of luck and persistence. But it doesn't take long for Hazen to strike geologic gold.
Whoa! Jeez, look at that.
That is amazing.
The trilobite.
Hey, look, there's another head there, another head there. Right. Two more. Boy, this is rich rock.
The trilobites here are amazing because these are the oldest animals you can find that are preserved as what you think of as a fossil that you can hold in your hand.
Some trilobites were like horseshoe crabs, scurrying about the ocean floor. The reason they're found as fossils today is because they developed an astonishing evolutionary trick: shells. Trilobite shells were made of calcium carbonate, the same mineral found in limestone, the rock that built the pyramids. In fact, life itself began to make rocks for its own advantage, and the idea went viral.
If you had a shell, you're going to survive a lot longer than that soft-bodied animal that doesn't have a shell. The trilobite had an advantage. It's survival of the fittest.
The trilobite's mineral shell heralded a new phase in the evolution of animals, catapulting our planet into the present stage. Green Earth, one that is rich in diverse life. From humans back to trilobites, we owe our evolution and survival to the world of minerals. With shells, then eventually with bones and teeth that paved the way for life to grow taller and stronger. All are evidence of life co-opting minerals for its own evolutionary advantage.
We've thought for centuries, animals, minerals, they're separate kingdoms, right? But it turns out they overlap, they're intertwined, they co-evolve, that life makes minerals, and minerals has led to new life forms. You can't separate the two. Life and rocks are totally intertwined through billions of years of Earth history.
One of Hazen's favorite places to see this intertwined history of life and minerals is at the Calvert Cliffs along the Chesapeake Bay. He and his wife Margie pick up shells and shark teeth from a time 18 million years ago when massive sea creatures swam here.
That's nice. Isn't that pretty? You find teeth along the beach that are 5, 6, sometimes 7 inches long with serrated edges, razor-sharp teeth. These were immense creatures. Sharks that may have been 50 or 60 feet long.
These giants of the sea would have dwarfed today's great whites, and it was the bones and teeth created with minerals that enabled them to grow so large and powerful.
They were feeding on whales. Dolphins would have been a snack.
They are just one small part of a story of coevolution stretching back to Earth's beginning.
The life, the rocks, it's all part of the same story.
Step by step, throughout Earth's evolution, minerals and life have sparked chemical reactions that have sculpted the planet into what we see today, and helped create the life we know.
At this place, you've got a sense of the immensity of time and the constancy of change. Life is creating and sculpting our surroundings in ways that are quite wonderful. And just recognize the power of life to transform a planet. Of course, humans transformed the planet too. We build cities, we build roads, we change the composition of the atmosphere, the colors, the shapes.
And they're the building blocks of modern civilization.
We wouldn't have televisions, we wouldn't have automobiles, we wouldn't have buildings without the mineral riches that we have.
But could rocks and minerals also solve the greatest mystery of all time? The origin of life.
The rocks we pick up tell a story that life couldn't have occurred without rocks.
Could cold, lifeless stone hold the key to every living thing on Earth? From Australia to Morocco, Nova goes around the world and back in time to investigate the origin and evolution of life.
Look at a rock and you think, oh, nothing. But this holds the signature of life.
From its first spark
People were saying they made Frankenstein in a test tube.
to the survival of the fittest.
These were immense creatures, sharks that may have been 50 or 60 feet.
Was it the secret link between rocks and life that made the difference? Life's rocky start, right now on Nova. The ancient market of Marrakesh, a chaotic, colorful gathering place teeming with life for thousands of years. The perfect place to ask, how did this exotic, beautiful, and sometimes bizarre thing called life begin? How did Earth go from a lifeless, molten rock to a living planet full of diverse and spectacular creatures? It's a question that has long perplexed scientists. Now, Robert Hazen, a geologist, is trying to show we are missing an essential ingredient in the recipe for life.
Look at that name, calcite.
Rocks.
Nothing seems more lifeless than a rock. It's inanimate. It's the antithesis of a living thing. But we're beginning to realize that rocks played an absolutely fundamental role in the origin of life.
Hazen is out to expose a secret relationship between rocks and life that helped drive both the origin of life and its evolution into complex creatures.
This is a very new set of understandings. And the more we look, the more we see that life depends on rocks, rocks depend on life. This has been going on for 4 billion years.
As a geologist, it's no surprise that Hazen is searching for answers written in stone. But is he right? Are rocks the missing spark of life? The history history of Earth is unimaginably long. If it were sped up to the equivalent of a single day, all of humankind, from the earliest skeletons to the invention of the iPhone, would have occurred in only the last 4 seconds. Dinosaurs were still roaming Earth about 20 minutes before that. But the creation of our planet occurred more than 23 hours earlier, 2 cycles on this clock, or 4.5 billion years ago. Comprehending Earth's vast history is a formidable task.
There's 4.5 billion years of change, but you can divide it into half a dozen ways of describing Earth through time.
Bob Hazen has come up with another way to visualize Earth's long history that reveals this special relationship between rocks and life. He has divided it into 6 stages, each represented by a different color. To understand how we ended up with green Earth, the planet we now know, requires us to turn the clock back to before there was any life at all. Stage 1 was the creation of a black Earth. Back in Morocco, Hazen and Adam Aronson, a meteorite expert, seek out a small rock from the beginning of our cosmos.
Wow, look at this pile. Yeah.
These are meteorites, rocks that have fallen from space.
This is Tamdach. This is the one that fell 20 kilometers up the road from here. People saw it fall.
A recent meteorite fall in Siberia was captured in videos that have shown up on YouTube. Other space rocks have ended up for sale here in Morocco.
So you buy this without doing tests?
I'll drop the cash right now if you give me a good price.
Meteorites here can sell for tens of thousands of dollars. That may seem a steep price for a lump of rock, but these are some of the very oldest objects in our solar system.
This is the oldest object you could ever hold in your hand. It's 4.6 billion years old, and it was formed before Earth formed. This is the very first solid material, the very first rock in our solar system. And these came together to build all the planets.
Our Earth was created out of the rocks and dust present at the start of our solar system. Over time, small fragments of orbiting rock collide, come together into the planets circling the Sun. At first, Earth was molten with temperatures in the thousands of degrees. But in the whole vacuum of space, this hot rock began to cool and change. Nothing, not a speck of dust, is believed to have survived from the period of Black Earth. It was a hellishly unpleasant time. Volcanoes spewed hot lava from deep inside the planet. When it cooled, it covered Earth with its first rock, called basalt. And it was black. It seems like a desolate landscape. But some ingredients that life will need are already here in these rocks. Look inside and you begin to understand how intriguing even an ordinary rock is.
Every rock, you slice it open, you look inside, there's something special.
Rocks are made up mostly of minerals, which are crystals like quartz or diamonds. Looking through a microscope at super thin slices of a rock lets you see its mineral composition. This is the rock peridotite, made up of small crystals including olivine and pyroxene. Even a simple black basalt rock spewed from a volcano becomes a patchwork of colorful minerals.
It's sort of like a fruit cake. You know, slice it open, there's nuts and there's dried fruit and maybe some lemon peel. It's made of lots of little things, and it's not until you slice into that fruitcake you see all the stuff inside that makes it special.
What makes them special is not only their beauty. Minerals have remarkable chemical and physical properties and are a source of many of the elements, nature's building blocks. That is why they're essential in our modern world